Hello everyone, my name is Jeff Shaw, and today I'd like to talk a bit about a seminal paper that I found. It's about extraction summaries. It's from the literature, other journal articles, and so on that would do so. Now the journal article that I picked was by Luhn, and it was the automatic generation of literature abstracts. Now Luhn used to work for IBM, and he's very well respected. Now, the reason I chose this paper is because it was seminal. Now, I had to find it by going through a rabbit hole of sorts of other papers. I found a paper that was cited by a paper that was cited by a paper, and so on until I finally got to the point where I found Luhn's work. And it's been cited 2,708 times, which is really high. Now, what's more important is that the articles that have cited Luhn also have high amounts of citations, which shows that there's a high impact for this paper. Now, it also seems that this is the first paper that has really looked into text summaries in this way. There's really almost no references in this work. Actually, the only reference is on another paper of Luhn's on computing methods, which shows that this research was very new for the time. And the last reason I chose this was because Luhn is so well respected at IBM. He has over 80 patents, he invented the checksums as well, and that's a way to make sure that numbers are in the appropriate place, you know, that there's no typos. Say if you were to type in a credit card number, using that, it would add them up. And then it would do a comparison of the digits to make sure that they did match up. If they don't match, then we can tell there's a typo, and that method is still used to this day. So, Luhn has had a high impact. Now, Luhn chose this topic because of a problem he identified. He felt that it was difficult to write abstracts. Now, way back when, in the old days, a lot of papers didn't necessarily have abstracts. You just kind of dive into the work. This was before papers were becoming standardized or commonplace. So sometimes a staffer at a journal printing place would have to write an abstract. I mean, this was nearly archaic. It's certainly not used at this point. But what ended up happening was that there were so many more publications in the scientific literature that it became overwhelming for staffers to keep up, and they just couldn't. Now, abstracts could have been influenced by the author's attitude, bias, background, etc. And if they wanted to have some kind of way to standardize and stabilize in an objective way their abstracts. So they thought, why not use a machine to automate such a process? So Luhn developed the following method, as you see on this screen. It's a 5-step process. First, the document has to be converted to a machine-readable format, and I'll talk more about that in a bit. Next, you had to count the words. There are words that are considered too common, and there's a table of common words that will be deleted, such as is, am, and, etc. And then that table was used to filter those words out. Now, once those significant words are capped, what's done is a measurement of significant words to see how close they are to one another in relation to the text. If the significant words are close, that increases their significance. But if the distance is farther, they're considered less significant. So they measured the distance and used that to assign a significant value to each sentence. Lastly, the sentences with the highest significant factors were then used to make an auto-abstract. They were pulled, and maybe the top 5 sentences then formed an abstract automatically generated. Now, the significant factors. There are 2 measurements here. The first is how often that word occurs, and the second is how close the significant words occur. If the significant words occur close together, they're considered more significant, and the opposite is true. What's reflective is the information content of the sentence. So to do that, you first have to figure out the significance of the words, and then build from there onto the second step, which is the significance of the sentence. So, how do we figure this out? The significance of the words and the impact of them. Now, the key words are often used repetitively. Now, Luhn made a very good argument. If a writer is trying to use synonyms when talking about a point, they'll run out. The other issue is that in technical literature, you have to use very precise jargon. It's not a good idea for an author to try and be verbose and flowery with their writing when they have the same meaning. Instead, the word will come up again and again. Now, another way to bin words is not dependent at all on the meaning. So, for example, we see here, the 6 different words that I have in quotes on this slide are all based on the root word, differ. And they're all considered to have the same meaning, but how does one catch those and put them into one bin? So we'll talk about that in my next slide. But really, you'll see in my last bullet, essentially it's an inventory of the words. So these are some examples. On the left here, we have 2 words, similar and similarity. The first 7 letters pair up. So we get the clue that they might be similar. Now the last 3 letters of the word similarity, that ity suffix, do not match the top word similar. So using the criteria on the bottom here, say 6 letters or below do not match, we can consider that there is a similarity. And you would put those 2 words in the same bin. However, there are some that fail this test. So if we look at the example on the right here, differ and differentiate. The first 6 letters do pair up. However, the last few letters of differentiate has 7 letters that do not match the first word. And that is above that cutoff of 6, meaning that those 2 words, although very similar in definition, are considered in different bins. So, that raises some questions for me. Now this is a graph to visualize the concept about how words are accepted or not in bins. So if a word is considered too common, you'll see on the left side of this figure, like is, the, etc., are caught by the table of common words. It may be that they do not add meaning, so they are considered cut off on that line that you'll see here, where that red bar is at the top. Now, conversely, on the right, we see the words that have low frequency. They don't add anything necessarily to significance, so they are not included. Now, we see that sweet spot right in the middle here, and that includes just the right frequency, it has a lot of the information in that sentence, and it is considered significant. So we're looking for that sweet spot. Now that we have the significance of the words figured out, we can calculate the significance of sentences. Now, it does not depend on meaning. It's 100% statistical in its approach. So if we have significant words in that sweet spot, right, and they're close together within a sentence, we consider that sentence to be more significant than another. So, we could have a sentence with a number of significant words. What has to be done to work at the sentential level is to see how many significant words are in the sentence. If 4 or 5 significant words are between, if 4 or 5 insignificant words are between significant words, it's considered not significant. If the significant words have less than 4 or 5 insignificant words between them, we do consider that sentence to be significant. Now with clusters, we have to have them primed by significant words on the left and right, and you'll see that in the next picture here. In this graphic, we have a sentence. It's wordless, but it doesn't necessarily matter. We see those dashes, which represent words. So the stars represent a word with significance. You'll see that the cluster is always bracketed by significant words on the left and right. So essentially, it's bookended. Now, the number of significant words in the sentence here is 4. We have to square that number and get 16. And then to further our calculations, we have to divide that 16 by the number of total words, including insignificant and significant words within the cluster. So 16 divided by the 7 total words, we get an answer of 2.3. Now that is a significant factor for the sentence. That is the significance factor for the sentence. And this is just a bit of a history lesson. So, punch cards are used to create the document, and then those cards are then transcribed into a magnetic tape. That magnetic tape then feeds into an IBM 704 machine, which you'll see in this picture here. Crazy huge. This thing is massive. It cost $2 million back in that time, and only had 12,000 flops. Now, today's computers operate in teraflops rather, and that's a big difference. It's always cool to, watch how much computers have progressed in just this short amount of time. So, some results. I took an article from the New York Times, and you don't have to read the article, but it's just talking about how there are new treatments from chemistry that can then help people with psychological illness. But what I do want you to read is the auto abstract to the right. Take a second to read through that and think about, on your own, whether or not that is a good summary. So at the very end of the sentence here, you'll see a number, and that's a significance factor. So what do you think? At the end of the presentation, I'd like to have you share your opinion. Let us know whether or not you think the auto abstract is actually reflective of the article or not. So let's talk about the impact of the paper. Edmondson wrote another seminal paper that looked at different methods to making those summaries for articles, but it described Luhn's methods and felt that it was good enough in its quality to continue in furthering the research. Now again, their approaches are 100% statistical. So I start to notice there's a bit of a flaw in Luhn's methods here. Now Edmondson did develop something later by introducing the log likelihood ratio, which, the importance of that to this day still is just unparalleled. Now, Rath did compare and say that Luhn's methods were too statistical in nature and did not include other factors such as syntax and lexicon and other linguistic factors that just weren't sufficient. But it was nice to have that, seminal paper that really opened the door for working and moving forward in this field. So this is a little bit of my critique. I don't see any code. I wanted to see some of it. The historical reason for my own benefit is just to look back and take a bit of a time travel. And, I'd also like to port it to a new language if possible and use it for my own work. But the cutoffs were also not provided within the article. The cutoffs for the too frequent were only in one experiment, and the other experiment didn't make note. Now, the table of common words were also not provided, which, we could probably figure it out on our own, but that means that you cannot 100% replicate that experiment, unfortunately. Now, there's also only one reference, and that previous paper, like I said before, I can't necessarily judge if it's good or bad, but it is. And it's also a very simple measure of the significance. Good and bad. Is it too simple? It's easy to understand, sure, it's easy to apply and then make a code for it, but the negative is that it might be too simple. But Len's argument was very well developed and defended, so I did like that aspect of it. These are my references, and that's all. Thank you.